Let me give little more concept on roasting before we proceed to material and heat balance. As I said earlier, that roasting is a unit process especially employed for conversion of sulphite to oxide in view of the difficulties that I have already enunciated. Now, one of the important thing in case of roasting is to predict the phases or number of phases which can form at a particular temperature. So, that information can be derived from the so called predominance area diagram. So, I will give little bit detail about the predominance area diagram. Now, as the name suggests, this predominance area diagram gives the information about the stability of a phase for a given partial pressures of SO2 and oxygen, and remember these predominance area diagram are constructed at constant temperature and pressure. Now, as I have said that when we apply the phase rule to the equilibrium of the phases and when there is a condensed phase and also temperature is a constant, then the degrees of freedom it becomes equal to 3 minus P. So, accordingly we need a 3-dimensional diagram if we want to construct predominance area diagram for MSO system, that is metal, sulfur and oxygen system, where PSO2, PO2 and temperature are the variables. But now, since if we take temperature also as a constant, then for a given temperature we can predict the equilibrium phases by considering the variation of PSO2 and PO2. Now, let us consider a system, for example, nickel, sulfur and oxygen system. Let us consider a system which is nickel, sulfur and oxygen system. Now, let me draw the predominance area diagram. So, these are the say the axes are here we have log of PSO2 in atmosphere, we have log of PO2 and the scales are say minus 20, say minus 16, minus 12, minus 8, minus 4 and here it starts from minus 12, then we have minus 8, we have minus 4, then 4, 0 and 4 and 8. Now, well these are just order of magnitude, the lines that I am going to draw that may not comply with the value of the axis that I have given. So, it goes something like this. This one, this is the one and then so these are the say variations. So, here the various phases are say this is nickel sulphide, this is NiSO4, this is NiO, this is nickel and this one is Ni3S2. Now, these diagrams is drawn at fixed temperature, at fixed temperature and 1 atmospheric pressure, and under this condition the degree of freedom F that becomes equal to 3 minus P. So, what we note from this figure, the stability of the phases. There are regions. So, I will just note down the points. So, let me take this is as A, this is at B, this is C, this one is E, this one is F, D, G and H. So, the diagram, it contains the variation of PSO2 and PO2. The variations are shown in terms of the lines, for example, DH, CD, BC, CF. Then the diagram also have the variance, the invariant point, for example, the point B, C and D, these are invariant points. Now, what does it mean invariant point? That means here the degree of freedom should be equal to 0 and all the three phases will coexist at a particular value of PSO2 and PO2. So, you see at point D the phases NIS, NiSO4 and NiO will coexist. At point C, NIS, Ni3S2 and NiO will coexist. At point B, NiO, Ni and Ni3S2 will coexist, and according to the phase rule, number of phase equal to 3, then degree of freedom is equal to 0. That means this B, C, D, these are the invariant points in the predominance area diagram. Whereas, the line say along the line CD or line DH, what we have? There are, say again, if the number of phases are 2, then we have degree of freedom F is equal to 1. That means, along the line the degree of freedom is equal to 1. That means, the NIS or NIO can be present at different value of PSO2 for a given value of PO2 or for different value of PO2 for a given value of PSO2. That is what the variation of PSO2 with PO2 along the line CD, DH, this means. Now, again say if we note, if we put for example, P is equal to 1, then we get F is equal to 2, that means degree of freedom is equal to 2, and these regions are represented by the area. That means, the phase NiO, the phase NIS and phase NiSO4 can exist for a combination of PSO2 and PO2, for a various combination of PSO2 and PO2. So, this NiO for example, it can exist at different value of PSO2 or PO2, and see several values of PSO2 and PO2 can make phase NiO stable. That is what the degree of freedom 2 means. That means, you have 2 degrees of freedom, you can change PSO2 and PO2 and get the phase, for example, NiO or NiSO4 or NIS. So, that is what the say principle of construction of these diagrams are means. Now, these diagrams are in fact constructed by considering the equilibrium values. That means, in the system NiSO, we have to consider all possible reactions which can take place, and once we consider all possible reaction, we have to know the free energy values. From the free energy, we calculate the equilibrium constant, and from the equilibrium constant we find out the variation of PSO2 and PO2. Of course, the temperature is constant. Also, in order to avoid the complexity, these diagrams are constructed by considering the activity of the condensed phase, that is equal to 1. However, if the activity is not less than 1, then the predictions about the phases made from these diagram has to be modified. So, what I am going to illustrate in the following is how to construct these diagrams to know the stability of the phases by considering that the activity of the condensed phase is equal to 1. So, let me write down first of all the reactions. For example, the line CD, if you see the predominance area diagram, the line CD represents the equilibrium between NIS, which is at condensed phase, plus 3/2 O2 gaseous phase, that is equal to NiO condensed phase plus SO2 gas. That is, line CD represents the equilibrium between NIS and NiO. So, if I write down the value of K1, as I said, we are putting it by taking condensed phase equal to the activity of the condensed phase is 1, that is the pure phase, then K1 that will be equal to PSO2 upon PO2 to the power 3 by 2. So, as such I can write down now log of PSO2, that will be equal to log of K1 plus 3 by 2 log of PO2. So, if I plot now K1 I know from the delta G naught values. So, I know how PSO2 varies with log PO2, this I can take various values. So, you see if you plot log PSO2 against log PO2, the slope of the line will be 1.5. So, that is how these diagrams are constructed. So, you place this line in the diagram. Now, we have to consider next equilibrium. For example, if you notice in the diagram the line BC, it represents the equilibrium between Ni3S2 and NiO. This equilibrium, these lines means, now I have to put it the equation Ni3S2 condensed phase plus 7 by O2 gaseous phase, that is equal to 3 NiO condensed phase plus 2 SO2 gaseous phase. Again I have to know the delta G naught values, and then I can calculate now K2, that will be equal to PSO2 raised to the power 2 upon PO2 raised to the power 7 by 2. So, if I put now log of K2 plus 7 by 2 log of PO2, that will be equal to 2 log PSO2. So, I have to find out relation between PSO2 and PO2. So, in this case log of PSO2, that will be equal to 1 by 2 log of K2 plus 7 by 4 log of PO2. So, again if you plot for this equilibrium Ni3S2 NiO equilibrium in a log PSO2 against log PO2 plot, then the slope will be 7 by 4. Now, then if I consider for example AB, the line AB, it represents NiO equilibrium. So, I will write down now nickel condensed phase plus half O2 gaseous phase, that is equal to NiO again condensed phase. So, K3, that will be equal to 1 upon PO2 to the power half. So, from here log K3, that will be equal to minus half log of PO2. So, you see NiO equilibrium is independent of PSO2 and hence a vertical line in the predominance area diagram for nickel sulfur oxygen system. Now, if you consider line GD, in fact an equilibrium between NiS and NiSO4. So, this is equilibrium between NiS and NiSO4. So, again I write down the equation, say NiS condensed phase plus 2O2 gaseous phase, that is equal to NiSO4 condensed phase. Now, if I write down log of K4, that is equal to minus 2 log PO2. Now, you see NiS NiSO4 equilibrium is also independent of PSO2. Therefore, you will also get a vertical line on log PSO2 versus log PO2 plot. Line DH. Now, DH represents NiSO4 NiO equilibrium. It represents NiSO4 NiO equilibrium. So, I will write down now 2 NiO condensed phase plus 2 SO2 gaseous phase, that will be equal to NiSO4 condensed phase plus O2 gaseous phase. Now these reactions which I have written, remember these are the stoichiometric reactions, that is an important thing, they are the stoichiometric reaction. So, we can write down K 5 that is equal to PO2 upon PSO2 2. So, we can put it now, we can simplify, that will come log of PSO2, that will be equal to minus half log K 5 plus half log PO2. So, that is how this equal. Now, again if we look at the line FC, now line FC represents the equilibrium between NIS and Ni3 S2. So, we have to write down the stoichiometric reaction, 3 NIS condensed phase plus O2 gaseous phase, that is equal to Ni3 S2 condensed phase plus SO2. So, we can write down now again log of K 6, that will be equal to PSO2 upon PO2. So, we can write down now log of PSO2, that will be equal to log of K 6 plus log of PO2. That is how the equilibria between NIS and NIS3 S2 goes. Now, the last line EB, it represents the equilibrium between Ni3 S2 and Ni. So, we can put the equation Ni3 S2 condensed phase plus 2 O2 gaseous phase, that will be equal to 3 nickel condensed phase plus 2 SO2. So, if I write down K 7, that will be equal to PSO2 power 2 upon PO2 to the power 2. So, if I simplify and rearrange, I get log of PSO2, that will be equal to log of PO2 plus half log K 7. Now, say these are the, what I mean to say here, say these are the various equilibrium values on which the construction of the diagram is based. That means, now from the literature one has to obtain the value of delta G naught for a respective reaction. If not available, then we have to determine the values, and from the value of delta G naught one can find out the value of K. Then one can plot this diagram and one can know, well, these are the stable phases at a particular temperature, which will depend upon the variation of PSO2 and PO2. Now, here a caution is needed, because these diagrams, well, at the present what I have illustrated, there I have taken the activity of the condensed phases is equal to 1. In case when the activity is not equal to 1, then the pressure variation will shift according to the magnitude of the activity coefficient, that is represented by the deviation from the ideal behavior. So, what we have seen from here, that the phase NiSO4, if you look to the predominance area diagram, is possible under highly oxidizing condition, whereas the reduction of NiS or Ni3S2 to nickel is also possible, but under highly reducing condition. So, like this, these information can be obtained from these diagram. That means, I just note down 2 or 3 information, that means Ni3S2 2 nickel based on the predominance area diagram is possible under highly reducing condition, under highly reducing condition. Whereas, if you want to convert nickel sulphide to nickel sulphate, say NiSO4, then it possible at high PSO2 and PO2. You see this diagram, it is on the extreme right side NiSO4 is exist. But in practice the nickel sulphide is converted to nickel sulphate through the following route: nickel sulphide first converted to Ni3S2, then converted to NiO, and then converted to NiSO4. Now, this is now one prediction that is made by the diagram, that is possibility of NiS to NiSO4 is possible under highly reducing condition, but then again it comes the economic feasibility. So, economically it is done NiS, Ni3S2, NiO and then to nickel sulphate. So, that means these information they are to be modified by the practical considerations. Now, in some say roasting operation, the metal forms several oxides and also sulphides, basic sulphate and sulphate. For example, say in some roasting the metal forms several oxides, metal forms several oxides and also sulphides, sulphate. Now, for example, the system lead, sulphur and oxygen. Let us see the predominance area diagram of lead, sulphur, oxygen, because lead is also an important metal and the lead also occurs in the sulphide form. Let us see the roasting in PB, S and O system. I again just put the predominance area diagram for this predominance area diagram for PB, S, O system. So, this diagram it looks. So, again I am plotting here for example, log of PSO2 against log of PO2. Left side is highly reducing and right side is gradually proceeding towards oxidizing condition. So, the sum of the phases that goes, well I will note down the time, say the sum of the magnitude say minus 11.5, where here is minus 8, minus 4 and 0. So, here I put for example, minus 7, let me put somewhere here is minus 2, then minus 1, 0 and 1. So, this is minus 1. So, this is what it goes. There are the various oxides that can form. These are the say various oxides, say this portion is for lead, this is for lead oxide, this is for PbSO4 and this region is for PbS. So, this one is PbSO4 into 4 PbO, this one PbSO4 into 2 PbO and this one is PbSO4 into PbO. Now, normally in roasting the lead sulphide ore, the gas composition lies somewhere in this particular region. This is the gas composition during roasting. During roasting operation. Now, some important information that we can derive from here. The first of all, this PbO, it can form several basic sulfates. It can form several basic sulfates like, as you note from here, PbSO4 PbO, then PbSO4 2 PbO, and PbSO4 4 PbO. That means, if our objective is to convert PbO to PbSO4, then it goes through PbSO4 4 PbO, then 2 PbO, and then 1 PbO, and then ultimately to lead sulphide. Second important thing is that PbS and PbO do not have a common boundary. If you note the diagram, do not have a common boundary. Do not have a common boundary. That means, roasting of PbS will always form PbO and PbSO4. When PbS and PbO, it does not have the common boundary, and if you carry out the roasting, then there will always be formation of PbO and PbSO4. So, that means, dead roasting of PbS is difficult. That means, dead roasting of PbS to PbO is difficult. I mean, this you can easily explain from the predominance area diagram. Had there been a common boundary, then it would have been possible, but since there is no common boundary, so it suggests that PbS to PbO will always have the formation of PbSO4, and that is what in practice it is also there. Third important point that you note from here, that sulfatizing roasting of PbS to PbSO4, it can be done, but PbSO4 is insoluble in water. Now, this is with reference to hydrometallurgical extraction, because in hydrometallurgical extraction you want to dissolve the metallic part into the solution, and once if the PbS convert to PbSO4, then PbS is difficult to dissolve. So, that information is important from that point of view. Now, fourth important thing is that PbS to lead is possible by controlling PO2 and PSO2. That means, this reaction PbS condensed phase plus O2 gaseous phase, that is equal to Pb liquid plus SO2 gaseous phase. So, this reaction is also possible. So, what I have illustrated from the predominance area diagram, the process of roasting. Under what condition what phase can form, that will be dictated by PSO2 and PO2 ratios for a given temperature. So, this information can be very easily derived from this diagram, and if we see the roasting practice, if we follow the roasting practice, see the roasting practice. Now, the roasting practice, it depends upon the metal to be recovered from sulphide ore. It is not always that you convert all sulphide into oxide, no. The technological feature will also decide whether it is required to convert all sulphide to oxide or not. For example, in the production of copper, it is not desirable that all sulphur of the ore should be converted to oxide in the roasting stage, because the technology is like that. It is not because the technology demands that copper sulphide should be retained till it is present to the copper production stage. Whereas, if you consider the production of zinc, the production of zinc, it demands that zinc sulphide should be completely converted to zinc oxide, that is called the dead roasting. So, what I wanted to illustrate from here, that it is not always necessary that you convert all sulphide into oxide during the roasting stage. It depends on the technology for a particular extraction of metal. Now, in essence, since all non-ferrous ore, they contain iron in it. So, one of the important objective of roasting is to convert FeS to FeO, so that it can be removed during the metal production stage. Now, in that process, for example, in copper extraction, when you want to oxidize FeS to FeO, then in that process some of the sulphide of the copper also gets oxidized to CO, although the objective is not to convert sulphide to oxide. Whereas, in case of zinc sulphide, you want dead roasting. So, well, iron is also easily converted to oxide. So, these are some of the things that the technology demands, how much to be converted, how much sulphur to be converted to oxide. So, another important technology of roasting, that is called sinter roasting. Sinter roasting. Now, the sinter roasting is in fact a combination of sintering and roasting. Now, in certain extraction processes of metal, particularly from sulphide ore, where blast furnace is used, there the physical state of the roast product is also important. So, in the sintering roasting, the ore concentrate is sintered as well as simultaneously roasted also. And this sinter roasting is required when fine ores and concentrates have to be agglomerated, before they can be charged into a blast furnace, into blast furnace. Now, otherwise what will happen? Lot of dust will result. Now, this particular sinter roasting is typically used in production of zinc, in imperial smelting process, which uses blast furnace to produce zinc from ore concentrate. So, this is about the sinter roasting. Now, sometimes what happens, say in the roasting of complex sulphide ores, the oxides may react with another, may react with one another, and typical example is in the roasting of zinc, the oxide formation like ZnO Fe2O3. So, it is also required that which type of what conversion is required in the roasting of sulphide concentrate, that will depend upon the condition of the production of metal or the type of ore that is required for the production of metal. So, that is all I thought for this. Now, I will give the reference that you may consult for the dominance area diagram. Say you can consult the book H. S. Ray, R. Sridhar and K. P. Abraham. On extraction of non-ferrous metals. Non-ferrous metals. This is the East West Press Limited. So, that is what. Now, if you have some questions, I think I can answer those questions.
Yes, sir, I have some. Sir, is roasting necessary for all grades of copper concentrate?
Well, it mostly depends on the practice, but practically it is found for low grade copper. Say if you have low grade copper means if you have copper say less than 25% and high FeS then roasting is necessary. Because the whole idea of roasting is to convert FeS to FeO. So, that FeO can be removed in the subsequent stages. But even if for high grade ores, say for high grade ores, for high grade copper ore, where copper is say somewhat greater than around 30%, well, some practice does not do roasting, they directly proceed to the smelting operation. So, it is not always that you carry out the roasting, it depends upon the grade of the concentrate. In case of copper, definitely if the grade is high, then you can eliminate the roasting stage, but in case the grade is low, then you have no option except to carry out the roasting.
Sir, what are the chemical reactions occurring during roasting of copper concentrate?
Yeah, during roasting of copper concentrate, several reactions are occurring. So, you want to know the chemical reactions. The chemical reactions occurring during roasting of copper concentrate. Now, there are several reactions that can occur during roasting that depends upon the partial pressure of oxygen. Depending on that, several phases can form CuO, Fe2O3, CuSO4, SO3, SO2 and so on. So, some of the reactions that I can give you, say for example, if we take now main mineral in case of copper ore is chalcopyrite. So, if I take now 2 CuFeS2 plus 6.5 O2, that is equal to 2 CuO plus Fe2O3 plus 4 SO3. Now, also one should see during the roasting that the higher oxides of iron should not form to the extent possible. because ultimately if you want to produce copper, you have to eliminate all oxides, all gangue, everything has to be removed. So, normally it is found that higher oxides of iron, they are difficult to remove as compared to lower oxides. For example, FeO can be easily removed by fluxing with SiO2, whereas Fe2O3 and Fe3O4 is very difficult to remove. So, that point also to be kept in mind. Another equation that can be, that reaction is possible, say CuFeS2 plus 4O2, that is equal to CuSO4 plus FeSO4, and the possibility of their formation you can predict by writing the delta G naught and K value, and you can find out what should be the PO2, so that this reaction is possible. Another possible reaction could be 2CuFeS2 that can react with O2, it forms Cu2S plus FeS plus SO2. Still another reaction could be 2CuFeS2. If I increase the amount of oxygen, say 4.5 O2, it can form Cu2S plus Fe2O3 plus 3 SO2. Then again another possibility is that 6 CuFeS2 plus 13 O2, that can form 3 Cu2S plus 2 Fe3O4 plus 9 SO2. Now, what I wanted to say, that several possibility of reactions are there, but in the practice one can control the PO2 and PSO2, so that the most of the FES it gets converted into FeO only. Some FES may be converted to Fe3O4 or Fe2O3, but the roasting is carried out such that the FES is converted to lower oxide and less copper sulphite is converted to oxide, because that will be a loss. So, in case of roasting of particularly for copper, the objective is to convert FES to FeO rather than Cu2S to O, CuO rather.
Sir, what are the applications of dead roasting?
Now, as I mentioned in the lecture, say dead roasting is in fact conversion of entire sulphide into oxide. It is not necessary that in all metal extraction from ore you convert all sulphide into oxide. For example, in copper extraction this is not done, whereas in case of, for example, in case of zinc, zinc concentrate, zinc sulphide is deadly roasted, zinc sulphide is deadly roasted. Converted to zinc oxide. So, any unroasted zinc sulphide, if it is a 1% zinc sulphide or 2% zinc sulphide, it is left in the roast product, then it is a loss of zinc. Now, the dead roasting of a particular sulphide to oxide, it is more or less, it will depend upon the reducibility of that oxide with the easily available reductant of carbon. For example, the extraction of zinc from sulphide ore is done by dead roasting of zinc sulphide, and then the zinc oxide which form, it is mixed with the coal or coke, and then the zinc is produced. Now, similarly, in case of lead sulphide, as I said, the dead roasting of lead sulphide is difficult, because there is no common boundary between PBS and PBO if you see the predominance area diagram. But however, another important thing in case of lead sulphide, that the lead sulphide it fuses at around 800 degree Celsius. So, therefore, the control of temperature is also very important. The dead roasting in case of lead sulphide is rather difficult to achieve, because of there is no common boundary. It may achieve PBS to PBSO4 and then to PBO. However, certain amount of PbO and PbSO4 will remain in roasting of lead sulphide. So, it is not aimed at the dead roasting for lead sulphide, only zinc sulphide is deadly roasted for production of zinc via blast furnace route.
So, what are the conditions for metal sulfate formation?
In fact, the objective of roasting for hydrometallurgical extraction, you convert sulphide into sulphate, because sulphates are, some of the sulphates they are easily soluble in the leaching that you are going to employ. So, general the conditions for metal sulphate formation, the condition for metal sulphate formation is low temperature, and high PSO2 and PO2. Now, the sulphate formation it also differs from one metal to other. For example, the highest sulphating temperature is for lead and zinc. Copper and nickel sulphate formation it occurs at relatively low temperatures. So, it depends from metal to metal. Also, FeO to FeSO4 occurs at below 600 degrees Celsius. Now, direct conversion of sulphide, say direct conversion of sulphide to sulphate, that is also possible, but at relatively low temperatures.
So, can you explain phase rule in application to roasting?
Well, I have already illustrated the phase rule. Now, phase rule is a very important rule. It gives the number of phases, or it relates the number of phases, degree of freedom with number of components. Now, in general, the phase rule illustrates P plus F that is equal to C plus 2. Now, this is a very important rule which determines how many degree of freedom exist for the coexistence of phases for any component system. Now, for example, if our system say have metal, sulfur and oxygen, there is a 3 component system. Here P number of phase, F is the degree of freedom, C is the number of component, then P plus F that is equal to 3 plus 2. Now, 2 they are coming because of the constant temperature and pressure. Now, in roasting normally the phases are condensed, so there is no effect of pressure. So, accordingly we have P plus F that is equal to 3 plus 1. Now, normally roasting is carried out at constant temperature. So, in that case the phase rule becomes F that is equal to 3 minus P, that means this is at constant temperature. Now, from this relation it helps to construct the predominance area diagram, because now you note from here that for if P is equal to 3, then degree of freedom that is equal to 0. So, normally when you have taken the temperature constant, then the variable remains PSO2 and PO2. So, if P is equal to 3, F is equal to 0 means in a diagram which is constructed by plotting PSO2 and PO2, you will get an invariant point. You have to get an invariant point, which means that at that particular point all three phases can coexist. Now, P is equal to 2, P is equal to 2, F is equal to 1. That means, two phases can coexist for degree of freedom is equal to 1. So, this representation will follow a line in a diagram, and for P is equal to 1, degree of freedom is equal to 2. So, this particular situation will correspond in a diagram in terms of the area. That means, you have 2 degrees of freedom, you can vary here PSO2 and PO2 to get that particular phase. Along the line, you can vary either this, either PSO2 or PO2. At a fixed point, you cannot do anything. At that point, all three phases will coexist. So, that is what the phase rule means.
Thank you, sir.